Hello, and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 1293, shortest path in a grid with obstacles elimination. At the time of recording, which is at the end of March 2022, this is currently Google's #1 most asked interview question. I know I put up a video maybe 2 months ago that was a different question that was Google's most asked, but they tend to change their questions quite frequently, so now this is the new top question. So if you have an on-site at Google, chances are you're going to see this question, so definitely one to know. Before we jump into the actual problem, please subscribe to my channel. I have the goal of reaching 1,000 subscribers by the end of May, and I need your help to get there. So please subscribe so I can keep making these videos and helping you guys get those nice coveted jobs in FAANG. That being said, let's read the question prompt. You are given an m by n integer matrix grid where each cell is either a 0, empty, or a 1, obstacle. You can move up, down, left, or right, and to an empty cell in one step. Return the minimum number of steps to walk from the upper left corner, 0, 0, to the lower right corner, m-1, n-1, given that you can eliminate at most k obstacles. If it is not possible to find such a walk, return -1. Okay, we read the question prompt. Now let's think about how to solve this. So we're given a grid and we're told that we want to find the shortest path. So this should immediately yell to you that we need to do some sort of a breadth first search. And if you haven't already seen my video on the shortest path in a binary matrix, go watch that video because it's going to lay the foundations of how we want to set up our breadth first search. And if you're not familiar with how to do it, then this problem might seem a little bit confusing. So go watch that one first and then come back to this one and you'll have a better understanding of how to set up a breadth first search through these like grid or matrix type problems. So what we're told is that essentially we want to start up here and we want to end down here. And we want to find the shortest path, but we're allowed to eliminate some of these obstacles, shown in red here. So what is the shortest path? So let's think about the base case where we're not actually allowed to remove any obstacles. So basically we would just have to find whatever the BFS shortest path from our, top left to our top right. But obviously this isn't the most optimal path because it takes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it would take 10 movements to reach it. But in reality, say we're allowed to eliminate one obstacle from this grid, right? In that case, well, we would just eliminate this one. So we would go here. So that's 1, 2, 3, 4, 5, 6. So now we could reach it in 6, which is actually our optimal solution. If we tried to remove any other ones, we would either get 6 or a higher number. So what we essentially want to do is we want to do a breadth first search, but this time we need to eliminate obstacles, and we're going to be given, let's see, a number k, which tells us the amount of obstacles that we can eliminate. So what we want to do is basically try our BFS as we would normally, and when we see an obstacle, if we still have, obstacles allowed for us to remove, so if we haven't used our budget of k yet, we can remove that obstacle and then add it to the queue to be processed further. Otherwise, we have to explore the other directions that aren't in that queue. Now, notice here that we're going to have different paths, right? If we start here and go here, then we haven't used any, obstacle removals. But if we start here and go here, we'll use one obstacle removal here. And if we somehow end up back at this square, this technically is a different path. Because even though we've ended up at the same square, the path that we took to get there is different. And we need to account for this by, in our scene set, which is going to be how we make sure that we don't actually go back on ourselves, is we're going to actually maintain a state of, oops, you can't see that. We're going to maintain the state of the current row, the current column, and the current K that we have when we reach that tile. Because reaching this tile up here with 0 obstacle eliminations is going to be different as if we started here and ended up at this tile, but we removed 2 obstacles, right? That's a different path. So to keep track of these paths and to make sure that we don't, discount paths and think that we've seen them before, we need to keep track of whether or not we've reached that, row and column combination with a given K. And this K is going to tell us whether or not we've been there with the current eliminations that we have. And if we have, that means that we can disregard this path because that means that we've already visited it. So we're going to need this scene set to basically just make sure that we haven't, been there on the current path. And essentially what we want to do is we're just going to do our standard breadth first search. And in this problem, we can actually only go, up, left, down, or right. So what we want to do is we just want to do our standard BFS. If we see a obstacle and we actually have a budget left for eliminating it, then we can basically remove it and then just keep going with our BFS. Otherwise, we can't add that path to the queue for further processing, and we have to ignore as if we could go into that tile because we could remove the obstacle there. So what we just need to do is our standard BFS. If we have a budget, then we will go into that square that has an obstacle. We will decrement our budget, add that to our queue for further processing, and essentially we're going to try to reach the end by just going through obstacles, using our budget here, and then as soon as we hit the end, that will be guaranteed our shortest path, because remember, we're doing a breadth first search. So breadth first search through, you can think of this grid as an undirected graph. It will give us the actual shortest path. So once we reach the target here, we can simply return how many steps that we've taken so far. At that point, that will be our answer. If our breadth first search ends and we haven't found any solution, that means it's impossible to reach the end, and we simply return -1 like the problem says. Like for this example, if we were given a budget to remove only 1, then obviously we can't reach the end here, because we would have to remove at least 2 in order to make it to the end point here. So for this problem, we would return -1 because it's not possible with a budget of 1. If we had a budget of 2, then we could go here, 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 and that would be a total path of 1, 2, 3, 4. But in the case that we have a budget of 1, obviously we have to break through these obstacles, and we can't because there's at least 2 required to get to that other path. So that's what we want to do. Hopefully that's clear. If not, once we go into the code editor, I'll break things down line by line, and this problem should be really easy. It's marked to hard. It's really not that bad. If you know how to do these breadth first searches through grids, this should be a really straightforward problem. So that being said, let's go to the code editor. I'll walk you through the solution line by line, and it should click for you. It should be really easy, and then you'll know how to solve Google's most asked questions. So I'll see you in the editor. Okay, we're in the code editor, and it's time to write the solution for this problem. Usually with these grid type problems, we need to keep track of, where our position is relative to kind of the rows and the columns of our grid. So let's define some variables to help us with our solution. So we're going to say rows is going to be equal to the length of grid, and the cols is going to be equal to the length of grid of 0. And we're looking for the target. So let's define a variable to keep track of the coordinates of our target, right? So target is going to be equal to the bottom right corner. So this is going to be equal to rows -1 and cols -1. So now what we want to do is we want to handle a bit of an edge case. If you think about it, the shortest path in our grid, if there were no obstacles, would be simply to go all the way to the right and then all the way down. The reason for this is we can't actually go diagonally, so this Manhattan distance is going to be the shortest path in the case that we have no obstacles. What about the case where we have enough obstacles to eliminate K that we could actually just take the shortest path? So even if this was all obstacles, because we have K eliminations, which equals the length of this path, we could just take the shortest path. So that's a bit of a edge case here. So we're going to say if K is greater than or equal to rows -1 plus columns -1, which is essentially the length of this path up from the top left all the way to the right and then all the way to the down. So that's going to be essentially the length of the rows and then the length of the columns. If we have K, which is greater than or equal to that path, then we can simply take this path. So we can just eliminate all possible obstacles along this grid and take the shortest possible path that we know. In this case, we can just return whatever that length is. So we'll say rows plus columns -2. And then obviously the -2 is just, if you did -1, -1 here. So basically just spreading this out. So that's going to be a little bit of an edge case. Now let's actually set up our queue to process this. So we're going to say queue equals collections.dec, and we want to initialize our queue with two variables. The first variable is going to be the total number of steps that we've taken on our current path. So obviously this is going to be 0 because we haven't moved from the origin. And the next is going to be a tuple, which represents the current state of our path. Remember that we need to keep track of our current row, our current column, and the total number of obstacle eliminations that we've made on this path. Remember that if we reach a tile again, it's not technically considered seen if we have a new number of obstacles eliminated on the path that it took to get to that tile. So for example, like we went over, getting to this tile, starting from the left, there's no obstacles removed. But if you went down, then right and up, technically you're in the same place as this other path, but you've actually eliminated 2 obstacles. So your path is different because you've removed obstacles. So the state of your, BFS is not the same. So you can't count them as the same and consider it as a seen tile. You can only consider it seen for a similar path, which is that the rows and the columns match, and you've eliminated the same number of obstacles on that path so far. So that's why we need to keep track of our current row, which is 0, our current column, which is 0, and then obviously we haven't eliminated any obstacles, so our state is just going to be k, which is the no number of obstacles we can eliminate. Now what we need to do is set up that scene set. So we're going to say set, and we're going to initialize it again with our current rows, columns, and the k that we've removed, right? So it's going to be 0, 0, and k. All right, now we can actually write our BFS. So we're going to say while q, and then let's unpack our item that we need to process. So we're going to say steps, and then we're going to have our current row, our current column, and our steps taken is going to equal q.popLeft. And now what we're going to say is if our current row and column actually equals to our target, then we know that we're done. So we're going to say if row col equals to target, then we can simply return steps taken. Oops, sorry, this is not steps taken. This should actually be k, which is going to represent the k that we have remaining. So let's see, removal, let's just call this removals left. Yeah, that's probably better. Okay, cool. So that will be, the number of removals left. Steps taken. Okay, cool. We're back on track. Apologies for that little hiccup there. Okay, so this part we were just checking if we're actually at the end, then we can just return the amount of steps. And okay, this is not steps taken. It should just be steps. And then what we want to do now is we essentially need to go in all 4 directions. So let's define a variable for that so we don't have to define it every single time we go through the loop here in the while loop. So let's say directions equals to what? It's going to be equal to, so this is one of the paths we can take. Then we go 0, 0 minus 1. We can go 0, 1, and that should be all 4 directions. Yeah. So we're going to say for row increment, column increment in directions. What we're going to do is we're going to say that the new row is going to be equal to the current column, the current row plus the row increment, and we're going to say the new column is going to be equal to the column plus the column increment. And now what we want to do is we want to make sure that actually the new column that we're moving to is within the bounds of the grid. For example, if we were at this position here and we tried to go right, obviously that would be outside of the grid. If we tried to access anything at that index, we would get an index error and our code would blow up. So we need to make sure that we're actually within the bounds of our grid. Otherwise, we can't actually move to that tile. So we're going to say if. So let's double check that our row is valid. So new row is within the bounds for our rows. And we need to check that the column is also within the bounds for the columns. So essentially less than or equal to 0 and less than or equal to cols. Then we know that we have a valid position. And what we want to do now is check whether or not this is going to be a obstacle. So we're going to say the new removals is going to be equal to the old removals. So however many removals left we had starting this iteration, minus whatever value is at that new row column index. So for example, if we were moving here, then obviously this would be represented as a 1 because it tells us that obstacles are 1. So we need to decrement our removals by 1 in the case that the tile that we're moving to is actually an obstacle. So we're going to say grid, and then we're going to say new row, new column, and that will take care of our new removals. Obviously, if we're moving to a tile that doesn't have an obstacle, then our removals left will stay the same because we're just subtracting 0, which is just going to keep it the same. So now we need to keep track of what our new state is. And then the state is, remember, our row, col, and the removals left. So the new state is going to be equal to whatever our new row is, the new column is, and whatever our new removals is. Now what we need to do is just make sure that our removals is actually greater than or equal to 0. If we've used up all of our removals, then obviously we don't want to continue on this path because we can't continue anymore. We've used all of our removals and we're not at the end, so therefore this won't be our optimal path. So we want to say if new removals is greater than or equal to 0, and the new state that we're moving into, or the new tile that we're moving into, is not already been seen, then we want to actually explore it. So we're going to say n new state not in seen. Then we can add it to basically our queue for further processing. So we're going to say scene.add new state, and then we need to add this to the queue. And remember, the queue is going to be populated by the steps and then the tuple representing the current state of our iteration. So we can say steps, queue.append steps plus 1 and new state. So we're going to be adding that tuple there. So that will basically be our BFS. Either we're going to find our shortest path by reaching the end within our BFS here, or this while loop will break because queue is no longer valid, aka there's no more processing to do, which means we were not able to reach the end. Therefore, we simply need to return -1. So let's submit this, make sure we haven't made any bugs, and I'll just run this because it was just to make sure. And okay, cool. It doesn't seem we've made any bugs. And excellent. Our solution is accepted. So that's going to be the solution. Now let's think about the time and space complexity for this algorithm. Okay, the last thing for us to do is think about what the time and space complexity of this algorithm is. So typically for a breadth first search, our time complexity is going to be big O of n, right? Because in the worst case, we would need to basically visit every single element in our grid. And this is still true, but now because we have k obstacle eliminations, we can actually visit every single grid, every single tile in the grid k times, because each time we visit it would be with a different number of obstacles left that we can remove. So this is going to be big O of n times k. And the reason for this is, again, we can visit every single tile in the grid, and we can visit it actually up to k times to represent the number of obstacles we can get. Remember that we're basically keeping track whether or not we've been to a tile by keeping track of the row and column combinations and the number of obstacles left. So that's the reason why we have to multiply it by k to account for the fact that we can visit a tile multiple times, and it's only counted as a unique path is if the k is different. So we're going to say that our runtime complexity is going to be big O of n times k. And our space complexity is similar, right? For a standard breadth first search through a grid, it would be big O of n, but because, again, we have to keep track of those k possible paths due to the fact that we can eliminate k obstacles, it's also going to be a big O of, n times k solution. So that's going to be your time and space complexity for this algorithm. This is the breadth first search solution. I believe there is a more complicated A* solution. We're not going to be going over that one today. We're just going to be sticking with the BFS. This is probably the easiest way to solve this problem and should be accepted in your interviewer. I think it just shows that you have an understanding of how to do breadth first searches and able to handle the edge cases of actually eliminating these obstacles. So that's going to be your solution. Hopefully you enjoyed this video. Hopefully, if you get this question in a Google Onsite, you'll now know how to solve it. And you can pass the interview, get that sweet job, and you can thank me later when you're working at Google. So that being said, if you enjoyed this video, please leave a like, comment, subscribe. If there's any other videos you'd like me to make, please leave it in the comment section below and I'll be happy to make those for you guys. Just let me know what you want to see and I'll make the videos. Otherwise, thank you for watching again and have a nice day. Bye!